Hi, 我是王博老说班导. Today I'm gonna give a different flavor of my talk. I try to pretend to be a sniffing spot. I explain what spot is later about hybrid bonding, interconnects, HBI in this talk. I like to assume I'm kind of a consultant in a way to explain the content of this talk. All right, it starts just to as an icebreaker, a spot or Scooby Doo. The Scooby Doo, it's very cute, but knows nothing, right? It's just a cute cartoon dog. But Spot is kind of cute and is know everything. Scott is what I meant. On my left hand side of the graph is the robotic dog that is sniffing in a in a huge factory. And let's look at what it's doing and give you a flavor. I think that's enough. This is a new robotic dog, Spot. His name is Spot. It's a robotic dog that is sniffing around with a lot of sensors in his head, and then he could detect many different things in different area of this factory or in a very harsh environment. And that's what I'm trying to do here. Let's do a little bit sniffing around. And then the sniffing means that the dog is nervous. I think I'm right now a bit nervous right now. Try to explain to you if I were a consultant. All right. Let's look at the what's going on right now with Intel i9 and Ryzen's 9 AMD. Which one is better? And just uh, look at the news. This is what the Howard Time tried to compare the advantage or the disadvantage of these two products. If you look at it, i9, it's i9 is here on the bottom two, and then the Ryzen 9 is on the top two. It's obvious that Ryzen 9 has more event. It's a 20 to 30% more advantage over Intel i9. And we want to explore why that happens, right? That's the part of the purpose of this talk. Why it happens. Okay. If you look at the AMD 3D chiplets, it's not exactly a chiplet that I know of, but they call it chiplet, it's fine, right? They package everything together on a interposer, silicon interposer with TSVs that everybody has right now, except the way they bond. It says that it bonds with direct copper bonding, which is hybrid HBI, hybrid bonding per se. So it has very clear copper to copper bonding. They claim a 3x power reduction for the 25% speed improvement, which we saw. This is almost 2021, right? But the product we saw here does reflect that performance. Okay, and then why is that? If you compare the AMDs, they call 3D V-cache. 3D V-cache is the way they connect. All right, that's their trademark. They name it a 3D V-cache, and I think to me it's like a level 3 or level 4 cache. Right? If you look at the L1 cache, it gives each individual core process small instructions as shown in the graph on the left-hand side, all right? The CPU chip, all right? You have the cache here, okay? L1, L2, L3, and then you have memory. And then the L4 sometimes come into play. It depends how you want to attach to it. So it's the higher the level means the slower the speed that I connect to. L1, of course, is like it's the fastest SRAM stuff. It's very fast. And then the way they connect L2 and L3, the cluster of cores is larger, and then it's slower because it's further away from the center of the core. But it still occupy a reasonably large area of a CPU. But now they claim they could stack them up together. This cache, they could stack them together. The cache die, they say it's L3, all right, 64 meg is L3. But to me, because externally it looked like the L4 to me, but doesn't matter, right? It's just how you interpret them. And then the bottom one has 8-core Zen 3 CCD. CCD is complex core die. And so that's where the CPU or GPU is, right? So this, you stack them up so you can access the memory. And that's the reason you got fast speed improvement. So you can see that the direct copper to copper bonding, all right, or hybrid bonding per se, that give you this speed improvement. That's I think, the key advantage. Then it's obvious that they've been working with TSMC, right? So TSMC make that for them. That's the only hybrid and copper bonding that I see from all these three foundries: Samsung, Global Foundry, and TSMC. And let's look at what they do in terms of, and then if you want to understand that, of course, the first step you do is to go to this TSMC, the SOIC system of integrated chip, SOIC. That everybody trademark their process technology, just like AMD do a 3D V cache. They claim they have a patent on it. I don't know what it's patent about, but it's strange to me that it's just enabled by a copper bonding, right? That's everybody knows. So then it does not have the novelty of a patent, but people can patent everything these days. And the patent, probably the trade name, I have no idea, right? But it's enabled by the TSMC. So if you look at the TSMC, so the first thing you do is look at the TSMC website, right? So you come here, the what, why, and hows of TSMC SOIC, and then you browse through the system, and then you roughly get an idea what they're doing. They're 2.5D silicon interposer using a microbond. Even 3D IC, right? It's a microbond. They don't call it 3D IC anymore. They call them SOIC. And here, SOIC bond is obviously a hybrid bond interconnect. It's HBI. So that's I call HBI. They don't say it, right? But that's obvious to me. Okay. And then you can see that SOIC, here you have micro bond here, and this is not copper. This is just some kind of tin alloy, and that, of course, resistance is high and the size is large. You can never be able to densify it too much. So it's solve that problem, see, with a direct copper connect. Right? And an advantage is obvious, right? Just denser. And the bonding density is much, much larger, and then speed is faster. Power consumption is much less. So overall, they claim a 10x speed, 199x bandwidth, and then the efficiency 20x. So all this combined to me is huge, right? Like 38,000 advantage. Okay. Now, so the figure of merit, if you compute all three together, it's like 38K. So, I mean, you probably won't get that, but you get the idea, right? And the other one interested to me is that the frequency response, right? The frequency response versus the signal loss, and then the microbomb is very obvious. These are applied material data, and you can see solar bomb and the microbomb. This is signal loss per dB. This is going to be uh, with the hybrid bonding is much better, right? So that's another good reason why people move to couple bonding. And you can see that the couple bonding, uh, it's it's getting look like a backend line copper. That's where you're going to go eventually at the end of the day. With that in mind, that the AMD, and we're comparing again the AMD chip, right? AMD chip versus the i9. But if you look at the i9, I'm not even sure that the i9 is made with as a Foveros process or not. You probably made with the EMIB process from Intel. But even so, if you look at the Foveros technology, currently they still have micro bond, but where's copper? I don't see that, right? I don't see from this graph. Uh, they still have not materialized or realized that their so-called copper technology for interconnect. But they do, but they publish a paper. If you look at the paper, right? If you look at the paper of the 2022 last year's IDM paper, they did have it. They did have it. They call it enabling next generation for 3D heterogeneous integration, right? There's a hybrid bonding interconnect paper, and they're showing they have a very nice 3 micron pitch. It's very clear that if they did a good job, they should make it happen. And the author is from CR, and you know that this paper is he's probably working with the PDD and try to make the yield go higher. But unfortunately, that is not shown on the product yet. Otherwise, they will make a big announcement or something like that. I haven't seen that yet. Maybe they're working. I bet they're working 9 days on this stuff. Right? But obviously, they have been delayed. All right, the development is delayed, and it's behind TSMC. If you're looking at TSMC, it's not. They don't. I don't think they are in a 3 nanometer. They probably in a much higher pitch. But then I saw a report about 9 micron. Later, I will show that to you. So this paper showed they are more advanced in terms of research, uh, better. I mean, faster than TSMC, but their HVM is not yet ready. So that actually is not a very good sign to me. The way I see it, that you need to have very solid baseline of something easier, right? Something easier. And if you don't have it, then you move to a faster node. I mean, tighter pitch. Sometimes can go bite you. Okay. So basically, why we want to go direct couple bonding or hybrid bonding is because TSV scaling is kind of getting lazy. TSV can do more, but microbond, you can see that the microbond, the TSV, you don't have to you can't get denser, right? You cannot denser because you cannot squeeze it. You have to attach to a microbond. So in a way that the microbond limitation limits you, right? So that's how I feel about this direct bonding could also help to drive the TSV scaling. So they talk about the direct bonding or hybrid bonding. That one of the advantage of that, right? Of course, there are many advantages. Smaller dimension IOs, pitch interconnect, but also help TSV to do further scaling. And that is a huge. I think that is huge. And then if you look at this, people try to, okay, they do the best they can. They try to squeeze it, all right? So they do, they could do 5 micron, 3 micron, or TSV, and then they have the 20 micron pitch for the bomb, 7. They try to squeeze as much as they can lately, right? I met these guys, right? But they hit a wall, right? They hit a wall. And these are all, I would say, small scale pilots. Doesn't really matter. Doesn't It's not very useful for the HBM, high volume manufacturing perspective. And my message I want to convey is that the micro bomb has not caught up with the point where TSV can be fully utilized. So you say you could do 7, but that's on the paper, right? It's not HBM. If you look at TSMC, TSMC will start to do, as they say, right? 9 nanometer is they're going to hit the market with their 9 micrometer pitch. And that's that obviously they don't want to keep squeezing this one because the variability, the NSPC control is not there to support the high volume manufacturing. These are good for publication, right? They are not for HBM. The real thing is you look at TSMC is doing exactly, and that gives you a picture. So, and that the transitions of the HBM, high bandwidth memory stack to SOIC, right? So that's what I try to do. Because if they could do it, they could really densify it and make it happen. It's they could make it 4 stack or 5 stack or 8 stack. That's at their leisure. Depends on how good the process can be. I think TSMC do a good job by enabling their couple bonding at 9. At 9, I think it's easier compared with if you look at the Intel, they shoot at 3. That's a 3 times tighter, an order of magnitude in terms of area. And I think that's more challenging, a lot more challenging. It's good to have something easier to start with because in this business, in this process technology business, you really need to have a good baseline. Otherwise, and then with the easier node, right? That look at the TSMC 7, 5, 3, and no, they never want to go to gate all around until 2. I even thought they would do 2 with the gate all around. The reason being, if they could squeeze the last juice of FinFET, they would do so. If you compare that with the Samsung, who want to go into gate all around structure at 5, 4, without taking the full advantage of 3, and FinFET at 3, they got dinged because of that, right? They got low yield, and because they lost the baseline. Okay, all around you don't have a baseline, and that is a hard one to overcome. So with that in mind, I want to say that the microbump pitch limit at 9 is obviously TSMC view from high volume manufacturing perspective. On the research side, you can do whatever you want, right? But you can make 1 die, 2 die work. That's meaningless. It's not useful, right? So we're talking about size. Pitch size matter. Does pitch size matters? Of course, matters. But the matters, I think, is in other ways. So how do you have a die attachment that can meet the spec? So this is from the Bessie. Bessie, they have this table about driving enhanced capability, advanced height attachment. They are the equipment company that come out with a spec, right? For all these different process technology, this accuracy they require, okay, throughput they want, and then the working area, right? So this is from the HBM perspective. Okay, so gradually they go from 5 to 10 micron to 50 to 400 nanometer, 3 sigma. So this is what you need to look at. Look at the tightest spec, the 50 to a 500 nanometer for 3 sigma. So each sigma, it's like less than 20, right? It's 17. So it's very tight control when you're placing a bonding either wafer to wafer or die to wafer. And that's the challenge. And that the mechanical precision is, that one can never be done in a research lab, either from Leti, either from the IMEC, or that. You had to done from the real high volume manufacturing side, around thousands of wafer. This is we're going about 5,000 chip per hour. These kind of speed, all right, and then you can get true data. Right? So when you look at the unit here, thousands chip per hour. Without that, you cannot even make money, right? So this is the table that's interesting from an HBM perspective. Right? Then there's going to be a die size matter. So if you look at how they stack dies, right? You stack many dies here, then and then you want to make sure the bonding are good for every one of them. So the accumulative yield from your bonding has to be perfect. If you lose couple, it gets you're dead, right? And then remember that there's one key message here is a non-good die. Each die here, they are all good die. So which means that they've been screened out from the factory floor already. So the production die give you a die, a good die. And that good die come with a cost of that manufacturing process. And we know that for the say M5 is like 15,000 per die. So every die will cost you a couple $100 at least, right? So assuming this is $400 each, I mean $100 each, yeah, $400 beside and this and that. So this is a very expensive process. So the yield is very demanding. And then you can imagine that the larger the size, the die, the more costly of the non-good die. So does size matter? Of course it matters. It costs a lot of money to make a big die. Then if you look at the Gen 3D Vcache from the Ryzen 9, you can see the die size is getting larger and larger these days, right? Talking about 41 to 80. And then, of course, this one is smaller with the most denser. And so this, say M5 node, right? So this is where they all even M4, right? So I don't think this 7 nanometer, I don't think it's correct. So this 5 nanometer. And then you could see that the number of transistor is in the hundreds of millions, right? Then you need to know what is the yield of these dies. So I did a simple calculation in one of my videos to show you how it works. This is what I did in that video. I will show that video to you. We get it later on. I use the data that TSMC reported that their yield rate is 80% for a die with 1 by 1. If you use that data, you could have this this graph. So you have a yield, right, with this formula. Okay. And then you could see that here you have, say, yield die is 1, roughly 1, then the yield is 80%, right? 0.8. Then if you go with using this formula, that you can clearly see if you're 0.8, 0.6, then your yield is like 87, right? So this is what I meant. So the Ryzen 9 CCD complex die, this one, I'm trying to compute the die of this size, what is the yield? So if it's 0.8 here, 0.8 centimeter is here. 0.8 centimeter is this one. Has 81 millimeter square, right? If you use this formula, 0.8 is roughly here, right? So roughly 0.85, give or take. And it's 0.4 is 0.4 here. That is the 3D Vcache. And you can see that the yield number is 0.4 is about 0.91. So that's give you a feeling. So when you look at the die reported out, that you can see that when die size increases, the yield gonna drop by nature, by nature of this derivation, this formula. Let's give you another example. If you look at the NVIDIA Hopper H100, the die size is huge. It's 826 millimeter. All right, this is as I mentioned last time. This is almost reaching the limit of a field of a reticle. It cannot bigger than 558, and this is 526. Huge. If you use that formula to calculate, the yield is only say 30%. Okay, 30%. Pretty nasty. So that's why the TSMC had to run faster and feed more into the line to compensate for the lower yield. If they want to come up with the same number of good dies, they have to make a more wafer start to compensate that. And what they did actually was they recently announced a couple months ago to give their NVIDIA wafers a super hot run status. So they increase the speed 2x. And then in a way they could mitigate that loss. So I keep feeding the line with 2x speed, eventually come out with the same number of good known dies. Okay. So, and then the AMD Genoa is 5 nanometer. I calculated that what the yield should look like, right? And using a density, I think I calculated it's like 6.4 centimeter. And then the yield number is 34%. So the message I want to convey is that the larger the die, it will be smaller the yield by nature. And you cannot really improve it much. You could improve a little bit, but your baseline, remember, your baseline is this number, right? So 80% for 1 by 1. This is already world record. To be frank, this is already the best in the world. The other guy can't do that, right? I didn't hear Intel or Samsung doing that at all for this 1 by 1 die size. So you can see that the line, if you go push the yield up a little bit, right? So of course this line is still going to be a parallel line, right? So the trend is still there. Okay. And as I promised, so I would like to share with you about how I derive the formula with this website. I have you go search me. Yield is money. You search that, you'll find it, right? Because discussion of yield, and in there I discuss in detail how this formula can be derived. I have this statistical. This is based on some kind of statistical analysis. Equal to exponential minus 0.44 centimeter times 0.44, and times d0. D0 is just the constant that we're going to put into the negative binomial. Then you see that the D0 is 1.15 centimeters. Compare with the what's reported by TSMC. This example is, die size 0.44 to 0.44. And then I amp it up. I even make it bigger, right? So I make it 1 by 1 centimeter. I think this is old data. They probably improve it. So the die size has become larger now these days. So I artificially bump it up. So, this is just show how I derive this formula. Everybody can go in and using the data they obtain and do a similar calculation, right? So basically, what this says that the defect size, the defect, and then you will calculate yield. You have a critical area and a defect density. And defect density is proportional to exponential dropping down. But the critical area is not. Meaning that when you got the defect killed, the kill rate is saturated. Anything bigger than that is also been killed. Doesn't matter, right? So you time this probability together, you got this lambda, the actual distribution. That's where you see, and then use this statistical analysis. Then you find out that your yield is a negative binomial. The negative binomial per se is what the IRTS recommend. They suggest a different number of alpha, and 2 is the number come out. That's mostly commonly used, right? But that's fine, all right? So this just you have time and go to this video and take a look at it, right? So anyway, I force it. I said A3 is one by one. It should not be that big, but just assume that's happening. It doesn't matter because when you change the die size, you shift the line. It's always downwards. That's for sure. And then for the larger dies, that formula cannot even work anymore. And to be frank, but the trend is there. If you look at the FPGA is such a huge die, right? From the Xilinx is close to 9 centimeters square, and then you got one or two die from one wafer. That's what TSMC will sell you. That's what they sell you. One FPGA die is like $3,000, right, for the 28 nanometer technology. So the trending down for the yield is what I try to explain. This number is not a true number for us. And then I don't know what the number will be, but 30-40% is roughly the number you should get, right? So question of the day, what is the current hybrid bonding HBM status? Who's doing it? What's the roadmap spec? We just mentioned some of it. If you look at the roadmap, you could tons of roadmap on everybody, right? TSMC roadmap, right? So this one you could download from the web. They give you exactly what they're going. So SOC info and the info CoWoS, all these the important thing is the vertical interconnect densities, how many they could pack, and then they are in the year of 2020. Say here, we are here right now. We are here right now. Going forward, and this is what we're gonna see, and of course they are targeting all kinds of levels of cache, right, until the memory come in, and this is what's been interesting. Right? If you look at the more practical one, I think the IMEC one did a reasonably good job. The interconnect pitch, you look at the people are going this way, right? Going this way, and this why they're going this way. So right now is here, 2025. They assume that's what's happening, right? So they're looking at this range. Right. Now looking at this, I would say it's a micron pitch, around 1 to 10 micron pitch. That's why the message I want to convey from this graph. And then TSMC, another one, said that their goal is to do 2x per 2 years in terms of the density. That's what they do. So they look at the slope. They try to convey to the customer the interconnect density is calculated by Intel's formula, and they will try to do 2x per 2 years. It's kind of slow, but you can see how hard it is, right? It is not easy to do. And then the other one from the Dr. Yu Douglas, he's one responsible 3D roadmap, and you can see that maybe a chance of 3x per year to 2 years, right? This is what they promised to the investor, and I think this is the upside, their upside. And you can see that the contact packet pictures here, right, in order. You're amazed that these days Yeah, the back end line, I mean, not back end line, the packaging part is catching up with the front end. That's the scary one, right? The scary one. The contact gate pitch is here, you know. They're going that direction already. It's getting denser and denser. But so how to do it? And TSMC actually don't have they don't show exactly what they're doing. They put these three vectors. I'll say this all this the way forward 3IC advanced packaging. They want to put everything together. Is it the convergence or not? It's difficult to say, right? It's difficult to say. That they won't tell you exactly uh, where they're going, and they put every option here to try to confuse everybody. So and then all these 2D nanowire fancy stuff. I don't think gonna work, but you know they're there for the fun of it. And then the chip PKG or even PDK had to come together, so everything can come together. So this is their view. Their view of is all the technology going to converge into one. And if you found the driving force for the market segment, right? And this is the picture I like, right? So pretty much we just look at the AI core, which is the AMD. AMD come out with the new the Genoa, and then the Hopper from the NVIDIA. They are going to unify compute and memory core on core. So this one, the AI, they stack everything together. All the way they stack it, they have to go to, of course, the hybrid bonding, and then the SPM, they're stacking with the memory. But the FBM, everything is stacked all up. Everything here, they have to go with the hybrid bonding. Otherwise, the speed is not there. And you look at the competition of the Intel and AMD, you know that, right? Obviously, AMD is ahead. Let's go back to AMD, right? AMD with the direct bonding, they are ahead. And then if you look at the Intel, they don't have it, right? They have a good paper, right, on the hybrid bonding, but in the Foveros, they have not shown in here yet. I think they're going to show that, but it's kind of, at least I would say, delayed, right? That's what at least we can say. And in this foundry world, delay is a bad thing. You lost a customer, the customer go to the TSMC, and then you try to get it back. It's pretty hard. I'm telling you, it's pretty hard. So that's this side. And then application side, you still want to push that, right? Integrated silicon photonics and all that. The way you connect dies, you can make copper works. And that's really much more advantageous than the tin, all these kind of micro bond material. They're easy to do, but they cannot densify, right? So this is, I would call it, the driving force from the market segment is to follow the money. You just follow the money, right? But how do you follow the money? Follow money, I would say follow the money to see the truth. There are three ways to see this follow the money scenario. One is from DARPA. DARPA give you the right directions. They had tons of, far looking ahead professors, and then they will come out with, I would say, a lot of good stuff, right? I would say they point to the right directions. And you look at the CapEx, which is not just the CapEx of each individual foundry, but the CapEx of the supplier. I would say the scale supplier local support. That's what I meant, is that we are the outsider as consultant. We don't know what's going on, but we could do our sniffing around by looking at the supplier. I remember a story that I was asked a question about, is 3.5 going to work for the logic CMOS? And then there are tons of publications say it will work. But my answer to that question is, has anybody placed a big order of extron tool? because in order to make HBM, you need to run maybe you need to buy maybe 100 external tool, 3-5 tool, right? If you don't see that, then it's not happening. It's happening on PowerPoint. Okay, so what I meant is that using that learning, you can see that the scale of supply local support. If the supplier has a huge, supporting site nearby Intel or TSMC, right? That's meaning that the foundry is buying a lot of tool from them. And in order to make the demand, they had to increase the local size and the scale of the supplier local support had to be big, right? So, and then the third one is the defensive and offensive pattern and traces and trade secrets. Pattern are things they want you to know that they have it. It could be defensive and can be offensive. Defensive is one that they want to protect people from attacking them. So you are violating my patents. Says no. I have similar patents. The offensive one means that they're gonna put it into practice. They're gonna use that to make into productions, and that is the offensive patents. Both they need both. And trade secret is that the things they do, the nitty gritty things they do inside the process flow, that they don't want to patent it. They want to keep it secret. And look at the Coca-Cola. Their recipe has never been going into patent. Otherwise, they will lose that patent in 17 years. But Coca-Cola has been there for 100 years, right? So their recipe in concocting their drink are trade secrets. They could keep forever in that sense. So this they don't want you to know. That's what trade secret means. Okay. And then let's look at one by one. DARPA. DARPA had a chip program, right? The Common Heterogeneous Integration and IP Reuse Strategy. They call it CHIPS, right? They summarize the CHIPS. So DARPA, I think you know, right? You need to go to this website to, the DARPA. It is a DoD program. It's a defense program that accelerates the U.S. Process technology, right? So it's a DoD program. And not exactly. It's a big program that give you money, give professor money, and then they will look at 10 to 15 years away from us. So they come out with this the vision. The vision, right? It's they want everything to work together. Holistically work very well. And that's like this picture shown on their website, right? And they want everything to be aligned on and integrate any way a designer wants. And then so if you look at the recent publication, this one is worth mentioning, right? They have a sweet spot for the pitch. They claim that's what they say, optimum pitch. And here is packaging line, is SOC line. The pitch is for the pitch and the dialect. The dialect is the chiplet, right? Then that confuse each other. It's just a chiplet. Dialect chiplet size with this is ideal. Is ideal because they calculate the ROI here, right? It's not going to details, right? So there's a sweet spot. That's what they claim. Right, there's optimum dialect size, optimum pitch, right? They all come out. Whether you believe or not, that every factory is different, right? So they all own calculation. But the idea is there. They put all the variable here, and all these everything they could think of and come up with this optimizations of the interconnect pitch. There is a sweet spot, all right? And then to look at that with that in mind, Intel is 3 micron. All right, that's fine. Okay, they do have a 3 micron they're working on, and probably going to be in the market on the soon. All right, and then if you look at the TSMC, they already make a 9 micron work, which is one I think on the AMD Ryzen 9. So they're working on something more advanced, right? But how small? How small? Okay. And then I think the advantage over Intel by a couple of aspects. It's a big success, of course. The product is on the market, right? Meaning that it's high volume HVM compatible, and also mean they have a very solid baseline now. With that in mind, to move to another pitch is a lot easier. And Intel says they're targeting 3 micron pitch, but they don't have a 9 micron baseline. They're gonna hit it directly. This is risky. This is very risky. Okay, and then I don't know whether they're gonna success or not. We'll see. And then you look at TSMC SOIC roadmap, right? They come out with a report in the 3IC inside. And then they have said 0.9 micron. Wow. Wow. That's all I can say. They drop by 1 order of magnitude. They could really make it happen. It will be a huge breakthrough, right? You drop your pitch by 1 order of magnitude, which means that everything around it, either it's a wafer to wafer or die to wafer, the placement accuracy has to be in the sub 50 nanometer range. That is a challenging. So that's what I meant that the DARPA and the related stuff, and then that give you a direction to work with, right? And then let's look at the CapEx, right? CapEx, unfortunately, recently is not really good, right? It's corrections, but before that, it was going pretty good, right? So the CapEx give you at least the way the money goes. And then the percentage wise is the volume market share. It's a growth. It's been predicted. I mean, you look at everything. It's always growing, right? That's why you see that. Right? But I think the one key message I would like to see is that I would like you to know is that specs is more look like front end. Yeah, it's scary, right? That's the scary part. I think we're showing this picture with you that the contact base pitch, that's the front end line of the die itself inside how dense the contact pitch is. And now you are going there, right? You are going there. You are going there. So that's the message I think this one tells me. Okay. And then, so let's look at the support fab, right? Follow the money to see the truth. That's what I meant. And look at the size of the support fab. Then in this hybrid bonding business, there are 3 ways of doing it. The wafer to wafer, direct placement die to wafer, and collective die to wafer. So this pretty much they're trying to do. They're trying to do with a process they bound together. This is the yield. The hybrid bonding issue to overcome from HVM perspective are these 2, right? Which means the yield. You better don't have any voids. If you have voids, you're kind of dead, right? That's not good. And then the overlay, because if you don't overlay on top of each other, the die to wafer or wafer to wafer, there's a mismatch. And of course, if you go overboard, the mismatch become too large. You either lost the die or you lost connection. You create a high resistance here, then you're dead too. So the speed you claim you have is not going to work with a smaller connected area between 2 copper, right? And then of course the reliability. It may work in the beginning. When you finish the die attachment or wafer to wafer attachment, you cut it up and you look at it. It's perfect. Everything's perfect. But once you run for a while, your EM ratio. So you got electron migration. You develop in the weakest joint some kind of void, and that's because you run the same current through it. The current density could be higher in some area. Delamination, because the thermal stress, the stress between the copper's elastic thermal expansion coefficient is very large, and compared with the surrounding ceramics, right? SiO2, Si3, and 4, And then so you may develop some kind of crack, and it eliminates the tool, and you lost the die, right? Remember, on top and bottom, they have good dies. That's $100 below and above. Once you hit that, the whole package lost. Right? And copper confusion. I'm sorry, copper diffusion. It's not confusion. Apologize. That when they're getting too close, if the protection isolation layer between them is not strong enough, copper can migrate. Copper is a very good migrant. It migrates in a very fast surface velocity, unbelievable. All right, people, so that's why nobody had a ball to put copper in a contact directly with the channel. So your contact is always like non-copper, like tungsten and now cobalt. No one dares to put copper there because copper diffusion is too fast. It can uncontrollably fast. And then a typical process like this is a simplified 6 step. And so what people do, the hybrid bonding, is that the pattern with common insulator, SiO2, and then you plate and you copper plating and you polarize it and you plasma activate it. Because the reason for this is very key step, right? The reason being, if you have copper exposed to air or even clean room air, it will develop copper oxide quickly. Right? You want metal and you become oxide, then the bonding will be very different. The resistance is going to go high as well. You don't want that. So actually the plasma activation is kind of a clean. It cleans the surface and then it activates the surface to make it more easy to attach between themselves. So bonding actually, right? There are two bonding, oxide and oxide bonding and copper to copper bonding. It's hybrid bonding. Two has to work. It's just like one, right? So say, I want to copper to copper bonding. What do I need oxide to bond? Without a system oxide to oxide bond, then your copper to copper bonding will not last. You could bond, but it just won't last because the oxide bonding is not there. They will easily develop tons of cracks, right? And then even the stress will be everything on stress will be put upon copper bonding. It's not on oxide has to share that stress. Therefore, any two material together, you don't want to take all the load. But the problem is that how do you make it work? The first thing coming to mind is particles. You remember, this is back in the line. It's not like front in the line, copper edge, right? It's super clean. Here you have a back-end environment, and the clean room is not exactly high stringent. And then you have a lot of particle already sitting on top of each other. You need to clean them properly. And then so you do this CMP, right? You need to clean them too. And everything has to clean properly in order. Otherwise, you have a 10x probability of developing a void. Once you're developing a void with a large enough particles, then you cannot do, right? And the wafer wattage is critical too, right? If wafer watts, then how do you align two together for the wafer to wafer process step? And then you go eventually. So that's the CMP gonna hit you with the particle issues, and the wafer wattage gonna hit you with alignment issues, and then and then the bonding, of course. If you have a particle before you bond, they're gonna develop. They have a 10x probability of developing into a void. So all these steps require a super clean, or with the particle that is less than the critical particle size, right? Particle size. And I have shown you something with a particle in terms of yield with my YouTube video as well. as I explained to you in my YouTube video, that the particle size is like a bomb landing in London. Let me explain to you what I meant. At which area will be dropped inside this grid. So this is a probability come out. Right? This is a probability he figure out and using and then plot it here. So the one the real one is the actual, and then the one is the one predicted by the Poisson ratio, by the Poisson equations and Poisson distributions. Then you can see that image very well. So what's that mean? That means that actually it is a random event. The Poisson distribution assumes a random. So when German airplane come out to bomb the London, they don't have a specific target in their mind. They just drop it when they are reaching the area, just drop it randomly. So this means that to British military, you don't have to do anything specific. You have to warn the whole city, but you don't have to focus on specific areas because they are random. And then so therefore you could focus on the resources in a better place. Okay, so that's a very famous Poisson distribution examples. And if you use that if you treat that to see the world, we will do the same thing. What I meant is that contaminants and particles are landed on piece of wafer. It's just like German bombs on London. They are actually similar from the. Yep. So that's what I meant. The bomb, the particle landing on the wafer here, they are just like the German bomb landing on London, and they are random and they are not predictable. They're predicted in a Poisson distribution manner, but you don't know where they'll end, right? The Poisson distribution is a unique property of knowing it's coming, knowing the average rate is coming, but you just don't know when it will hit. So, but anyway, people use that model to develop a yield model. I don't know. But the message I want to convey here is that the void from the particles has a 10x probability of being developed if you don't remove the particle. That particle, if it's large enough, whether it's large enough, what do you mean by large enough? If a 1 nanometer particle size, it does not matter, right? Because you are dealing with 3 micron, you are doing with 9 micron pitch. And then your size is some micron. So if 1 nanometer landing on your copper pad, you don't really care. But if you're moving into 9.9 micron, then the particle size previously not important in 9, say if you are say 0.5 micron particle, you probably don't care in this area yet. But that 0.5 micron, if you're going to 0.9 micron pitch, that becomes a serious business. So meaning that you have to increase the cleanliness of your clean room and your tool one or more orders of magnitude cleaner, to get what you want. So that's how hard it is. And then there's something of Austria, because the two very famous wafer-to-wafer bonding supplier, the EVG group, and then the Betsy. They are all big players. They're all from Austria, and Austria pretty good at this, right? And the other company, like IMS, is very good company dealing with the multi-E-beam. Still from Austria. There's something going on with Austria that I don't know that made them so good in this. But if you want to, that's what I meant, right? If you want to see the money goes, let's look at the size of the support fabs close by. So if you look at the Bessie, oh no, I mean here, EV Group in Taiwan, huge, huge. And then you look at their technology, and then you look at their company, the ABG in Taiwan, and you could see that. And look at look at the size of the fab; it's huge. Right? And you look at technology, and you look at the hybrid bonding, and you could see that they have the direct placement die to wafer or collective wafer bonding or even wafer to wafer. It depends on wafer level, So they are good at this, right? So that gives you a feeling about what they are doing, right? Die to wafer or even wafer to wafer. Die to wafer probably the most advanced one is the hardest one, right? It is the hardest one. So and here, and you could see the advantage. This give you a good feeling about what they're doing in terms of their process technology and they all they are supporting lithography or inspection tool. And so this is, and they also provide many different kind of bonding, right? And so that's what they're providing to the TSMC or UMC, all these big boys, right? This is that's what I meant that looking at the size of support fab close by, you know what they're doing, right? And then Betsy, another big one as well. So uh, wafer to wafer and then it's not is die to wafer or chip to wafer, die to wafer. Okay, and so looking at the size, that's what I meant that the size of a supplier fab close to the foundry, you know how many tools there. You can roughly estimate, not exactly the number, but the scope of the tool they're selling to the foundry, because that's how they support their local site, a local fab, right? So you could have a feeling about who are the biggest supplier that relevant to the TSMC or Intel by looking at their supplier fab size. And that's the reason I mentioned that follow the money and look at the size of the supplier fab. And lastly, but not least, follow the money to see the truth about patents. Patents are very expensive. Right? Compared to TSMC, Samsung, Intel, if you can compare it, all right, the uh, the 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 patents of these three foundry, the big guys, TSMC, Samsung and Intel, and then to review their true intentions. And there are two type of IP, right? You have good to have defensive one, meaning that you are not going to use for production. The one who uses production are must have. Offensive one. Those one you are using it is a must have. Good to have defensive one is that somebody else may have some funky technology, then you think there's possibility that you might or might not use it. You want to have protect yourself around your key enabling technology with many small IPs that are quite good to have defensive one, right? And but if you know that by looking at these patterns, we can get a feeling pretty well. Right? And of course, the know-how are hidden in the trade secrets. You will not see it in your patent. They will not discuss it, mention it. Because patent just say, okay, I'm going to claim this, claim that to make my process work. But they're not going to exactly let you know exactly what they are going to use, which is know-hows are hidden in their trade secrets and partially in their IP as well. But the real one must be hidden in your trade secrets. And what are they? So I would like to do a pattern comparison, but not in this talk. This is too big a scope and too much work for now. But the idea is there. So in conclusion, I try to pretend to be a sniffing spot. I want to be a spot here. I don't want to be a Scooby-Doo. I want to be a spot. And I want to snoop around to understand from I provide you a methodology. So for you to go around and explore, and with the knowledge base providing in this talk, give you a chance to understanding especially in comparing TSMC, Samsung, Intel, from this perspective, and you will roughly know who's the leader and who is doing what, and then who have been supporting them, and that gives you a good feeling about my intention, right? All right, so to be a good sniffing spot dog. All right, that's about it. Thank you for listening to my blah blah blah. Thank you very much. Bye bye.